Now that we are familiar with the idea of the first derivative and the second derivative, now is a great time to look at how can we apply these in application problems. What kind of problems can we solve using these tools? And one of the most common, or one of the first places that you'll generally encounter this, is in physics when we deal with distance or position, velocity, and acceleration. Let's start with a few definitions and then let's dive into this. So first of all, position, S of t, and honestly, um, these notes use the S of S notation, but generally we're going to use D to represent distance or displacement, so you might see this as D of t instead. So just be aware of that right away. I'm not going to rewrite all these notes. We are going to use S, but just know in physics class you'll often see the word or the letter, the variable D used to represent this same concept. So first of all, position S of t is the location of an object at a value of time t. Velocity, V of t, is the rate of change of position over time. So velocity is equal to the derivative of position. And we can think about this briefly here for a moment, that position is measured in meters at a given time. So meters at some value of s. Velocity or speed is meters per second. And acceleration is the rate of change of velocity over time. So it's meters per second or meters per second squared. Sometimes it's helpful to think about the units right away as we try to organize these relationships in our mind. So position tells us where the location is at a certain time. Velocity is the rate of change in position over time, so change in meters over change in time, so meters per second. And acceleration is the rate of change of velocity over time, so change in our meters per second over change in time, so meters per second squared. Also, we know that velocity is the rate of change of position, so acceleration is the rate of change of velocity, which is the rate of change of position. So basically, acceleration is rate of change of position, or in other words, acceleration is the first derivative of velocity and the second derivative of position, or often we'll use the word displacement when we're talking about this in terms of physics. And let's take a quick look at a quick example of this here. Once again, if you take physics class, your teacher will probably walk you through this as well. So you may have seen this already. But basically, x and y. Let's take a look at a quick dt, or position time graph. And we're going to have the position of an object over time. So I'm just going to graph it like this. So let's have our position function. This is going to be my f of x, which is representing position. If I find the derivative, so let's just quickly sketch what that derivative is going to look like. Let's extend our axes a little bit here. I know if my first function is a quadratic to the power of 2, its derivative is going to be a linear function to the power of 1. So let's switch our color here. F prime x. And it's going to be something like this. So I know when there's a local maximum, my derivative has a value of 0. Oh, let's change the color there. So something like this. So this is my velocity of my ball. First one was the position. So basically we can think of this like a ball being thrown. The ball goes up, it comes back down. What do we know about the velocity? Well, the velocity is going to be, actually I did this backwards. Let's fix that. So what do we know about the value? It's positive, then it's 0, then it's negative. I drew that the wrong way. So we'll fix that real quick. Something like that. Let's update those labels once again. So my quadratic represented the position of the ball. My first derivative gave me the velocity of the ball. And what do I know about the second derivative? F double prime x. In this case, this gives us the acceleration of the ball. So it's the change in our change in position, or in other words, it represents the slope of our first derivative. We notice that the slope of our first derivative is constant and negative, and so the shape of our graph here is going to be just a straight line right here. If it's always the same, that means our concavity is always the same. And yes, if we look at our original graph, it's always concave down. So we're always going to have a negative value for our second derivative. And that makes sense. Once again, I don't want to get too much into physics here, but basically f double prime x, this is my acceleration. And it makes sense that my acceleration is always negative because, you know, if we're standing on the ground, and we drop a ball, what happens? It accelerates down at 9.8 meters per second squared. So things on Earth are always going to fall at a constant acceleration when they are falling due to gravity. And so it makes sense that our acceleration would be constant because the pull of the Earth is always the same, and negative because the ball is going down. So there's your crash course introduction to motion graphs and what it means when we connect, you know, the position of the ball and also graph its velocity and its acceleration on the same graph. And these are the kind of things that we can answer by knowing how to find the first and second derivative. Now we can figure out what is the velocity of the ball at any given point. We can figure out what is the acceleration of the ball at any given point. Now let's take a look at a specific word problem example. A chipmunk travels back and forth in a straight tunnel. The chipmunk's position, s of t, after t seconds is modeled by the function s of t equals negative 12t cubed minus 7t plus 3. Find the velocity and acceleration of the chipmunk as a function of time. First of all, let's make sure we understand what the question is asking us to do here. So first of all, what does it mean by modeled? Well, it means described. So this function describes the location or position of the chipmunk at any given time. Described. And we're asked to find the velocity. Well, I know if my original function is my s of t, my position, the velocity is going to be my first derivative. And acceleration is going to be my second derivative. So let's go ahead, let's write out our original function. Let's find its first derivative. Let's find its second derivative. So the position of my chipmunk is given by s of t equals negative 12 t cubed minus 7t plus 3. My second derivative, or sorry, my first derivative, which is going to be the velocity. So velocity with respect to time is equal to s prime of t, which is going to be, and just using our regular derivative rules here, we're going to get negative 36 t squared minus 7. And we can then find our second derivative, which is going to be our acceleration. So acceleration with respect to time is the first derivative of our velocity, is the second derivative of our position, is going to be 2 times negative 36 is negative 72 t. And once again, quick sanity check. We had a cubic or third degree function. First, and then we found the derivative. It was a cubic or second degree or quadratic function. And finally, 1 degree or linear function. So quick sanity check. Looks pretty good to me. Now let's answer some questions about the chipmunk. Which of the following statements is true? The chipmunk is moving in the positive direction after 2 seconds. Well, let's find out. What does it mean by moving in a positive direction? Moving in a positive direction means it's changing its position. So we want to describe the change in position. Which function describes change in position? Well, change in position, delta d, or I guess we're using s here. So change in position over change in time, that kind of sounds like velocity to me. And velocity is our first derivative. So let's take a look at our first derivative function and evaluate it at t equals 2. So we're going to have velocity evaluated at 2 is going to be negative 36 times 2 squared minus 7. 2 squared is 4. 4 times 36, or negative 36, is negative 144. Minus 7 is going to be equal to negative 151. And we aren't told what our units of measurement are. I don't know if it's meters or inches or centimeters or whatever. So we're just going to use units per second. Yeah, and we do know it's seconds because that is given in the question. So negative 151 units per second. And notice it's negative. Negative indicates direction. So that means it is moving in the negative direction. So remember, it's just like when we dealt with vectors. I have the magnitude, so they're moving at 151 units per second, but I also need to consider the direction, so that negative is important. So the question said, is the chipmunk moving in the positive direction at 2 seconds? No, it is moving in a negative direction, so this is a false statement. Let's take a look at number 2. The chipmunk is slowing down after 1 second. Well, what does it mean when we see slowing down? That means our velocity is decreasing. That means we're going to have negative acceleration. So slowing down is a change in speed. It's a decrease in speed. So it means we want the slope of our speed graph to be negative. So that means I'm going to have negative acceleration. So acceleration means we're going to use our second derivative. So let's use our second derivative. So acceleration at 1 second. And let's evaluate. So we have our function. Let's plug in the value. Equals negative 72 times 1 is just negative 72. And what do we notice? And let's not forget our units. Units per second squared. And so we're going to have negative acceleration, which means decreasing speed or velocity, which means we are slowing down. So the question was, is the chipmunk slowing down after 1 second? And we can confirm, yes, it is. And we've just kind of described broad trends here. We could answer more specific questions like, what is the if we had the units given? What is the chipmunk's velocity at 1 second? What is the chipmunk's position at 3 seconds? What is the chipmunk's acceleration at 9 seconds? It's defined for all these things. So we can answer all sorts of specific questions. We could make some graphs. And in fact, I would encourage you to once again pause here and try graphing these functions in Desmos, either just plugging them in directly or using your derivative machine. And once again, just get a feel for how are these graphs related? How are the shapes connected? How can I predict, or how can the features of one curve relate to the features of another? And how could I answer questions about the the chipmunk's position, velocity, and acceleration? Our next example here is looking at a freight train. We are told that a freight train leaves a train station and travels due north on a straight track. After t hours, the train is s of t equals 18t squared minus 2t cubed kilometers north of the train station for t's between 0 and 9. So this equation, or this function, accurately models the position of the train as a function of time for between 0 and 9 hours. Let's take a look at the actual questions we're asked here. Question A, find an expression for the velocity of the train at any time where t is between 0 and 9. Find the velocity of the train after 3 hours and after 7 hours. Find the acceleration of the train after 1 hour. So once again, remember, I'm going to have my parent function, s of t. I'm going to have my first derivative. Yeah, so remember this was position, or often displacement when you're in the science classroom. The first derivative gives us the velocity as a function of time. So we have the velocity. And the second derivative is the derivative of the velocity, is the acceleration. All right, let's find some derivatives, and we can kind of do all the work first. So let's find our derivatives, and then let's answer our questions A, B, and C. So first of all, position, s of t is 18t squared minus 2t cubed. I mean, technically this is in the wrong order. Our highest degree should come first, but it doesn't really matter. Our first derivative, s prime t, is my velocity, which is going to be 36t minus 6t squared. And my second derivative, which is going to be acceleration, is going to be 36 minus 12t. And once again, our quick sanity check. Does the degree of our function change appropriately? Yes, it was cubic, and then it was quadratic, and then it was linear. Looks pretty good. Let's try to answer our actual questions. So question A says, find an expression for the velocity of the train at any time where t is between 0 and 9. And I found my velocity equation already. So velocity as a function of time is equal to 36t minus 6t squared. Question B, find the velocity of the train after 3 hours. So we're just going to evaluate our function at t is equal to 3. So we're going to have 36 times 3 minus 6 times 3 squared. And I'm going to go ahead and use my calculator. 36 times 3 minus 6 times 9. It's 54. And this did actually ask an actual question, so let's have a concluding statement. Therefore, at 3 hours, the velocity is 54. And what are our units? We're measuring in kilometers, and t is measured in hours. So it's going to be 54 kilometers per hour. And remember, technically, velocity is a vector. It does need direction. We just have a positive direction here. So actually, we can answer that as well. So we know the direction is positive, and it said positive was north. So it's heading north. So we can just add north to our answer, because once again, velocity is a vector. We need the magnitude of that vector, and we need the direction. And the second part of question B, evaluate at 7 hours. So V of 7 equals 36 times 7 minus 6 times 7 squared. It's going to be negative 42. How can it be negative? Well, remember, it's a vector. Direction matters. Negative just means it's heading the opposite of north, which means it's going to be heading south. So therefore, at 7 hours, the velocity is, and don't write negative 42, just write the magnitude, 42, the units, kilometers per hour, and the direction, south. If you told me it was negative 42 south, that means it's going the opposite of what I see here. So it would be going negative south, which would be north. But it's actually going negative north, so to speak, which is south. So don't say negative 42 south, just say 42 kilometers per hour south. So it's heading back to the station. And finally, question C, find the acceleration of the train after 1 hour, so at 1 hour. So we're going to evaluate our acceleration function for t is equal to 1, 36 minus 12 times 1, which is 24. Therefore, at 1 hour, the acceleration is 24 kilometers per hour squared. And once again, Do we know direction? I think we can say north, because it's positive acceleration, so it's heading in the positive direction, which we defined as north. And because it's positive, that means that it's a positive acceleration, so it's going to be increasing in speed. It's getting faster still. And I think that's everything we had to say here. We've successfully answered all the questions. We've used our first derivative and our second derivative, and we've talked a little bit about the fact that it's a vector and that we need to use the directions in our final answers. Also, don't forget units, very important. I will take marks off if you do not include units for word problems like this. Let's move on to our next example. To dramatically advertise the effectiveness of a new football helmet, a melon is taped inside it, and the helmet is dropped from a tower 78.4 meters high. The height of the helmet, h in meters, after t seconds is given by the function h equals 78.4 minus 4.9 t squared until it hits the ground. Find the velocity of the helmet after 1 second and after 2 seconds. When will the helmet hit the ground? So first of all, our function here is the height versus time. So notice if we set our time equal to 0, this term goes away and our height is 78.4. So that's where that value comes from. And this value right here, if you remember in the previous video, I mentioned that acceleration due to gravity is negative 9.8 meters per second squared. And notice if we find our derivative here, we get negative 9.8 t. So that's where these values come from. So these are like realistic values here. These are the type of numbers you would see answering this kind of question in physics class. So first of all, we're just going to rewrite our function. And I'll kind of do that off to the side here, just so we have room for everything. So our position of our helmet is given by ht. Height as a function of time is 78.4 minus 4.9 t squared. And I mean, I could exchange the positions and have the higher degree part of the function first, but it really doesn't matter. And sometimes it's nice to have a positive leading coefficient instead of a negative, even though it's technically not proper formatting. That's fine. Let's find our first derivative. So if height is position, the derivative of my height or position function is my velocity function. So h prime t is velocity. And this first term goes to 0. We're going to have negative 9.8 times t. And what is my acceleration going to be? Second derivative, negative 9.8. And like I've said, if you're already familiar with physics, or like I've mentioned in this video and previous videos, when something is falling, acceleration due to gravity is always negative 9.81 meters per second squared. And that's the number we're getting here, so that looks pretty good. Question A asks us to find the velocity of the helmet after 1 second and after 2 seconds. So we're just going to evaluate the velocity function at t equals 1 and at t equals 2. Let's just confirm really quick though. This is in seconds. Is our original function also given in seconds after t seconds? Yes. And also quick note, height is measured in meters. It's very important to keep track of our units when we're answering physics questions or just word problems in general. So make sure you are keeping track of that as we go. Let's evaluate. Velocity as evaluated at 1 second is negative 9.8 times 1. So negative 9.8 meters per second. And what is our direction? Down. You can write the word down, or honestly, I just write the arrow pretty often when I'm answering questions like this. Next up, my velocity at 2 seconds. Negative 9.8 times 2, which is going to be negative 19.6 meters per second. Still going down. When will the helmet hit the ground? Well, we haven't really talked about how to answer this kind of question yet, but let's think back to our problem-solving method. Grisa. Think about what is given. I know the function that describes the position of the helmet. I want to figure out when will the helmet hit the ground, so I'm trying to find... Actually, let's take a step back. We're not wrong, I just want to phrase this a slightly different way. What are we given? Well, I know that the helmet is going to hit the ground. What do I know about the height of the ground? Well, the ground is 0. Everything we're talking about here is defined in terms of height. So I had the height function, then the derivative of the height function, and then the second derivative of the height function. So I want to talk about everything in terms of height. And what do I know the height of the ground? How high above the ground is the ground? Well, 0. So I want to find the time when the height is equal to 0. So what is our given? Our given is that height is equal to 0. Our required is the time. Do I have an equation? Yes, I have an equation relating height and time that we're going to solve, and then we're going to write out the answer. So let's go ahead and do that. I'm going to set my equation equal to 0. So h of t is set equal to 0 equals 78.4 minus 4.9 t squared. Remember, t is our variable, so I should not know its value yet. That's what we're trying to find out. Let's rearrange and solve. So I'm going to bring the 78.4 to the other side of the equal sign. So negative 78.4 equals negative 4.9 t squared. Let's divide each side of our equation by negative 4.9. And we're going to find that 16 equals t squared. That's nice and tidy. Maybe that's why we chose this height for our tower. And what is the square root of 16? Well, t is going to be equal to plus or minus root 16, or in other words, plus or minus 4. Think carefully about that answer. What do we know about this value? This is giving us the time. Can I have a negative time? Not really. Technically, we can imagine that if we started measuring at this point, and we're looking at the helmet falling, maybe it's not falling. Maybe it was thrown, and we just started measuring at the peak of the throw. So maybe we could work backwards to negative time and think about, when was this helmet being thrown or whatever. But that's not the case in this question. We're just told that it's measuring, it's being tossed from the top of a building. And so we're going to start measuring when our time is equal to 0. So I do not care about these values here. And in fact, this is inadmissible. So we're going to ignore the value when t is negative. That doesn't mean that that value is wrong. It just means that in the context of this problem, it doesn't really have a meaning. So it is not a calculation error. We just have to interpret our results in order to properly answer our question. So we did our given values, required, we had our equation, we've solved. Now let's write out our answer. Therefore, the helmet, I just spelled helmet wrong. I was thinking about the word hit. Helmet hits the ground. Therefore, the helmet hits the ground at t equals 4 seconds. All right, question C. The manufacturer's demonstration will be effective if the melon is undamaged after impact. The melon will remain intact if the impact speed is less than 30 meters per second. Is the demonstration effective? So once again, let's try to interpret and understand what is the question actually asking us to find. So impact speed is going to be the speed or velocity when it hits the ground. And from our previous calculation, we've already figured out when that is, at t equals 4 seconds. And we know that speed is the magnitude of velocity. And I know how to find the velocity. It's the derivative of the position function. And we already did that calculation earlier to make our life easier. So let's go ahead and use that value and let's do a calculation. So I want to find the velocity at 4 seconds. I know the equation is negative 9.8 t, where t is equal to 4. So I'm going to have 9.8 times 4, which is 39.2. Uh-oh. That's concerning, potentially. So velocity at 4 seconds is 39.2. And what are our units? They are meters per second. These are also meters per second, so we can compare directly. And this was a negative value. So the negative value just means that it's going down. So that means our velocity is 39.2 meters per second in the down direction. And so what is the speed? Remember, speed is just the magnitude of the velocity. So the speed is 39.2 meters per second. And we notice pretty quickly that that is greater than our maximum of 30. So therefore, the demonstration fails because the impact speed which was 39.2 meters per second, is greater than the maximum allowed in this situation, which was 30 meters per second. So you can begin to answer some pretty neat questions using basic derivatives. So this is why this is so neat. What we can actually do with derivative and second derivative and stuff is we can actually, just knowing the position of an object or just knowing the function that describes the position of an object, we can then begin to answer questions about when does it hit the ground? How fast is it going? What is its acceleration? So I find this stuff pretty neat, and hopefully you find it a little bit interesting too. Moving on, we have another example. In this question, we are told that a sailboat that is coasting with its sails down has a velocity as a function of time, equals 100 over 2t plus 1 meters per second. We have units. Units are important. Let's highlight that. At time t. Question A asks us to give a formula for the acceleration of the sailboat as a function of time. So remember, if I have s of t, that would be my position. And I don't have that equation in this case. We don't know the function that describes position. We do know the first derivative, though, which is v of t equals 100 over 2t plus 1. And so I can find the next derivative, which is my acceleration, and we'll find that in a moment. So I know how to find the derivative, but here's an interesting question to think about for a moment. What if I wanted to know the position of the boat and I only knew the velocity function? Could I work backwards? Yes, I could. I could find the antiderivative, or I could do integration in order to find that. That's not something we're going to cover in this course, so I might touch on it again briefly before the end, but just know that that is possible. If you have enough information, you can work backwards and figure out what was the original function that this is the derivative of. So just think that anti-differentiation or finding the antiderivative is a thing that is possible. In this case, though, we're just going to find the derivative. So let's take a look at A. Let's start with our velocity formula. Let's rewrite it so it's not a fraction anymore. You can use quotient rule. We are just going to go ahead and use product rule, though. So I'm going to have 100 times 2t plus 1 to the power of -1. And let's remember our product rule. Actually, I guess we're going to use chain rule here. It's like a constant multiple thing. So remember, f prime x equals g of u prime, or sorry, g prime u prime. G here is u to the -1. G prime is negative, U is negative 2, U is 2t plus 1, and U prime is 2. So it's usually helpful to kind of do this off to the side right away, as I've mentioned and modeled before. And it's just constant multiple, so the 100 is just going to hang out front there. So let's go ahead and do that. So I'm going to have 100 times G prime U, so negative 2t plus 1 to the power of negative 2 times my U prime, which is 2. So we're going to end up with 100 times negative 1 times 2 is negative 200 times 2t plus 1 to the negative 2. And as we've mentioned before, we want the positive exponent at the end. So we're going to say that our velocity is equal to negative 200. Use up that negative to bring it to the bottom. 2t plus 1 squared. So it's a little not nice because it's a rational function, but no part of that was particularly difficult. And now that we have the function, we can go ahead and use it. So question A just said give the formula. We didn't have to evaluate. We didn't have to solve for anything here. So A is done. It just asked for the formula. Let's take a look at B though. When is the sailboat decelerating at 0.5 meters per second squared? Well, deceleration, actually, sorry, we didn't finish A yet. My bad. We found the, yes, we did. I didn't match my notation. V prime T. This is why it's important to label things at the beginning so you don't get confused later. So this is our acceleration formula. All right, we're good to go. So question B, when is the sailboat decelerating at 0.5 meters per second squared? So decelerating, there's two pieces here. We're working with acceleration, and decelerating means it has a negative value. So in other words, when is my function going to be equal to negative 0.5 meters per second squared? So let's go ahead and set that up. Once again, what is our given? We're given a value for A. What is our required? We need to find the when, so the time. So Grisa. So our given, we're given A of t is equal to negative, because it's decelerating, 0.5 meters per second squared. I want to find the time. Do I know the equation? Yes, I do. Let's plug it in and solve. So I'm going to have negative 0.5 is equal to negative 200 over 2t plus 1 squared. Let's do some rearranging. Let's try to isolate for t. And so I'm not going to show all my work, but I'll show a number of the steps. I'm going to start by, I can kind of just shortcut flip these two terms. Basically, I'm multiplying each side by 2t plus 1 squared and dividing each side by negative 0.5. So I'm going to find out that 2t plus 1 squared is equal to negative 200 divided by negative 0.5, which means that 2t plus 1 squared is going to be equal to 400. And we can take the square root of each side. And I could expand and then just have a standard form of the quadratic formula and use the quadratic equation to solve. There's multiple ways of doing this. So if you choose a slightly different approach, that's fine, but I'm going to do things this way. So I'm going to take the square root of each side. So 2t plus 1 is equal to the square root of 400, so plus or minus 20. As we've discussed before, I don't care about, I better leave it for now. I know that time has to be greater than 0, but if I'm dealing with some, if my value is going to be greater than 20, the minus 20 might be okay. So I can't eliminate it yet. I need to leave it in. So let's keep rearranging. 2t equals negative 1 plus or minus 20. I can see now that the minus 20 will not be allowed, because if I did negative 1 minus 20 equals negative 21, I can't have a negative time. So because t has to be greater than 0, I'm going to drop that. I'm going to keep working up here just because I'm running out of room. So 2t equals -1 plus 20. And I could have carried the plus or minus through, but I wanted to make my life easy as soon as possible. We're going to have t equals -1/2 plus 20/2. So I divided each side of the equation by 2. T equals -1/2 plus 10. T equals 9.5, or t equals 19/2. And 9.5 is exact, so we could leave it, that's fine. But generally speaking, fractions are better. We are done our calculation, so let's just finish up with our answer. Therefore, the sailboat is decelerating at 0.5 meters per second squared at 9.5 seconds. And there we go. And finally, we're done our example questions. I just want to talk about other derivatives are related to this. So we're familiar with our first few derivatives here. So we've talked about position, and we understand, okay, so I can have some function that tells me the position of a ball or a boat or a helmet or whatever. And I can find the first derivative, and that's going to give me the velocity, and that kind of made sense. We're finding like the slope of our position graph. And I know I can find the second derivative, and that's the first derivative of the velocity, and that gives me the acceleration. What happens if I keep taking the derivative? What if I had some higher order function, like something to the power of 5, and then power of 4, and then 20x cubed, and then 60x squared, and then 120x, and then 120, and then 0. What if we could keep going? And it turns out you can. So these aren't used commonly. So you might not actually ever calculate these in class in physics in high school. Maybe if you do this in university, you'll see these. But basically, we can keep taking the derivative. So the first derivative of position is velocity. The second derivative of position is acceleration. If we keep going, the derivative of acceleration is called jerk. The derivative of jerk is called snap. And then scientists like to have fun too. So after they called it snap, they're like, well, we don't really use the other ones too often anyway. Let's give them a fun name. And so the derivative of snap is called crackle, and the derivative of crackle is called pop. And for anyone who's not from Canada, I'm not sure if you all know this, but basically there's a rice puffed cereal called Kellogg's Rice Krispies. And so one of their jingles is like, snap, crackle, pop, Kellogg's Rice Krispies. So that's supposedly the sound that the Rice Krispies make when you add the milk. We can also go in the other direction. I said before that we can actually find the antiderivative of things. So if I know the jerk, I can work backwards and find a function for acceleration. If I know acceleration, I can work backwards and find the velocity. And if I know the velocity, I can work backwards and find the position. I can actually take the position and work backwards. I can find its antiderivative, and that's called the absciment. Once again, this is not something that's used commonly, but I just want you to be aware of this. And I like to order this in the other way sometimes. So I like to think about like my position time graph. So it's got some shape. And I know that if I were to kind of work up, so if I find like so I have my position. And then I work like upwards, I find the slopes, then that gives me the velocity. And if I found like the slope of the slopes, then that's my acceleration. So I think about it as a upward working process. And then if I work, so I start at position and work upward, but if I were to work downward, then I think about being in the basement or the absciment. So just if you do want to memorize this list, just for fun or something you think you'll be using in the future. I like to think of it as, I start by thinking about my position time graph. If I work down, so to speak, I end up in the basement or the absiment. And if I work up, then I find things like the velocity and the acceleration and so on. So we're not going to actually calculate these things. I don't expect you to memorize this list. Just be aware that there are multiple different derivatives of the position function, which give us velocity, acceleration, jerk, snap, crackle, and pop. Or I can find the antiderivative. I can work backwards the other way and find the absiment. And that's about all that we have to say about how I can apply higher order derivatives to solve problems related to position, velocity, and acceleration.